In this video, we're going to look at how to name alkenes and alkynes. So with alkenes, notice the difference between alkene and alkane. So we've named alkanes already, which is all single bonds. Alkenes contain at least one double bond somewhere in the molecule. Alkynes contain at least one triple bond somewhere in the molecule. So when it comes to naming alkenes, and this is essentially the same for alkynes, but we're just going to look at alkenes for now. So you're going to name the alkene, you're going to end it with ene. So if you have ene at the end, that tells you that you have a double bond somewhere. If you see the suffix diene, okay, so diene, that means you have two double bonds. If you have triene, that means you have three double bonds somewhere in the molecule. Now, as you're naming, when you're looking at finding your parent chain, the longest continuous chain of carbon atoms that contains the double bond is the parent compound. So sometimes it's a little bit easier because if you see a double bond, that's going to be your parent your parent compound. So then the base name is the same as that of the alkane. So you have methane, ethane, propane, butane, so on, but instead your ending is ene. So the carbon atoms in the parent chain are going to be numbered from the end of the chain closest to the double bond. So your double bond is going to get priority in everything. So even if you have methyl groups or ethyl groups or propyl groups, your double bond still needs the lowest carbon number. So you want the double bond to have the lowest number. So for example, here we have this condensed formula. If we number across, there's two different ways we could number. We could go left to right, 1, 2, 3, 4, 5, or we could go the other way, 1, 2, 3, 4, 5. You always number the carbon where the double bonds start. So if I go left to right, it's 1, 2, 3, 4, 5. If I go the other way, it's 1, 2, 3. You always want it to have the lowest number, so this compound is going to be 2-pentene. So notice this tells us that the double bond is on the second carbon. It's between the second and third carbon. Then substituent groups are going to be named just like we named alkanes. So for example, if we have this compound, find your longest chain, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. So either way, our longest chain containing the double bond is 6 carbons. So that tells us it's going to be a hexene. Now, when you name this, though, it's going to actually be 5-methyl-2-hexene. Notice the double bond gets the lowest number. Okay? Even if the substituent has a higher number, the double bond always gets priority. If there are two double bonds, okay, the end of the name is diene. So for example, this, 1, 2, 3. Okay, it's 1, 2, 3. There's 3 carbons, so you're used to prop. So the name for this would be propadiene. There's really no need for numbers here because since there's only 3 carbons, we assume it's between the first and second and the second and third. So instead of saying 1, 2, propadiene, we can actually just say propadiene. This prop tells us 3 carbons, ene tells us double bonds, and the di tells us there are 2 double bonds. So for example, let's name this structure. So remember, just like with alkanes, find the longest chain first. Now you guys know now that your double bond gets priority. So that means this has to be in the parent chain. So we have 1, 2, 3, 4, or 1, 2, 3, 4. Either way, it's 4 carbons. What is 4 carbons? 4 carbons is bute. So notice that even though the longest chain is 5 carbons, 1, 2, 3, 4, 5, we need to have the longest chain containing the double bond, which is 4 carbons. So parent compound is going to be 4 carbons, so that's butene. Then if we number from right to left, 1, 2, 3, 4, that actually gives our double bond the number 1. And then an ethyl group is attached to the second carbon. This is an ethyl group. So now we have 1 butene, but now let's name our substituent group first. So we have 2 ethyl, 1 butene. You need this number in front of the parent name to tell you where the double bond is located. Now, when we have double bonds, we have to worry about something that's called cis-trans isomerism. These are geometric isomers. So atoms or groups of atoms are free to actually rotate around single bonded carbons. So they could actually rotate around if they wanted. But when two carbon atoms are double or triple bonded to each other, they actually can't rotate like that anymore. So looking at these two structures actually have the methyl groups bonded differently, which actually gives them different properties. So this is called cis-2-butene. This is called trans-2-butene. So when your methyl groups are on the same side, notice the way that it's drawn, your methyl groups are on the same side. That is called cis-isomerism. When your groups, I keep saying methyl because these are methyl, but it could be anything. It could be chloro, bromo, iodo, anything. Ethyl groups. When they're on opposite sides of the double bond, that is trans-isomerism. So notice the longest chain is still 4 carbons, but it's just the way that they're actually geometrically connected. Okay, so like I said, the cis isomer is the one with both identical groups on the same side of the double bond, while trans has them on opposite sides. And you can see by the melting point that they're actually different. Now, if you have a double bond, that doesn't automatically mean that you're going to have cis-trans isomerism. Sometimes you do, sometimes you don't. So here I gave you an example. Draw structures and give the IUPAC names for all compounds with the formula C2H2Cl2. Okay, so C2H2Cl2. Remember, your carbons are always going to be centrally bonded. They're going to be your central atoms because they always want 4 bonds. Because there are only 2 carbons and there are 4 substituents, there are 2 H's and 2 Cl's, there has to be a double bond in between there. So start with the carbon-carbon skeleton, so carbon, double bonded carbon, and place the H's and Cl's in all of the possible locations and then name the structures. So I want you first to pause this video and I want you to place the H's and the Cl's in every location possible on the C double bonded C skeleton. You should get 3 structures that look like this. And so you have the chlorines on the same carbon. This isn't an isomer at all. These are just chlorines on the same carbon. You have chlorines on the same side of the double bond but bonded to different carbons. And then you have the chlorines bonded to different carbons but on opposite sides of the double bonds. So now that you have these structures, I want you to see if you can name these. This first structure is 1,1-dichloroethene. So notice that I could really give either one of these carbons the number 1 because they're both connected to the double bond. However, if it's possible to give my other substituents the lowest possible numbers, then I'm going to do that. Now there's no need to put 1,1-dichloro-1-ethene because it's assumed that that's your first carbon because we've already said that in the chloro. Then our other 2 structures are isomers. So here we have cis-1,2-dichloroethene and we have trans-1,2-dichloroethene. Okay, so notice that we have cis-trans isomerism for the second and third structures. Again, if it's ethene, there's no need to put a number in front of ethene because it's assumed that we've put it on the same carbon. Okay, so now here's another example. Draw structures for cis-2-pentene and trans-2-pentene. So this one's a little bit different because it's not necessarily substituents that we're looking at. We're simply looking at how the carbons are geometrically bonded compared to the double bond. So we know that the double bond is going to be between the second and third carbon because it's 2-pentene. So we know here's my second carbon, so 1, 2, 3, 4, 5. So notice this first structure has all of the carbons on one side of the double bond. Here it's on the top of the double bond. In this other structure, okay, which is trans 2-pentene, I have a methyl group on one side of the double bond, and I have the rest of the carbons on the other side. Notice it's still 1, 2, 3, 4, 5. It's still 5 carbons with the double bond between the second and third carbons, but it's all about the location on the double bond. Now, the most important alkene reactions that you will see, and the reason that we're not getting into a lot of reactions, but polymerization is so important. You see polymers everywhere. Polymers are giant molecules that are essentially made from what's called a monomer. It's a small molecule. A very common example is the polymerization of ethylene to form polyethylene. And so this is a monomer. Notice you have a monomer, a monomer, a monomer. That's just one small molecule. And when you add all of them together, that's polymerization, and you make a giant polymer. So like PVC, that's a polymer. Styrofoam is a polymer. Different plastics are polymers. So you really see polymers all over the place. And polymerization is how we actually can take an alkene or an alkyne and form something else with it. So you have 2 example problems in here. The first one says draw the structure of 5-bromo, 4-methyl-2-hexene. So I want you to pause the video and I want you to try to draw this structure. So with 5-bromo, 4-methyl-2-hexene, start from the end. Okay, start from the right side, start from the parent compound and work your way back. So 2-hexene. Hexene tells us that we have 6 carbons. There has to be a double bond somewhere. Okay, and we know it's just one double bond because we don't see diene or triene. But then we see 2-hexene. So the double bond has to be off of the second carbon. So here I've made my parent chain. 1, 2, 3, 4, 5, 6. And then 1, 2. The double bond is after the second carbon. So then I have my parent chain. Now I'm just going to put my functional group or my substituents on. 5-bromo, so off the 5th carbon. 1, 2, we already know the numbering. 1, 2, 3, 4, 5. Bromo, 4-methyl. 1, 2, 3, 4. Draw your methyl group. Then the next example says name the compound with this structure. You have this structure. So I want you to pause the video and I want you to see if you can name this structure. So as you name this structure, remember, start with your parent chain that contains the double bond. So I have 1, 2, 3, 4. I have 4 carbons in my parent chain. The reason I know to go straight across is because I have 2 double bonds here. So I have 1, 2, 3, 4. You always name the carbon that comes right before the double bond. So it's 1 and 3. So 1, 2, 3, 4. 4 carbons is bute. It's going to end in ene because there's double bonds, but it's going to actually be a diene because there are 2 double bonds. So it's going to be 1, 3 butadiene, but now we need to also name this substituent. So 1, 2, 3, 4. The reason I'm numbering that way is because not only is it giving my double bonds priority, but it's also allowing me to give this methyl group the lowest number. Because if we went the other way, 1, 2, 3, 4, notice I'd still have 1, 3 butadiene, but now my methyl group would be off the 3rd instead of the 2nd carbon. So 1, 2, 3, 4. So 2-methyl, 1, 3 butadiene. Okay, now with alkynes. Alkynes contain at least 1 triple bond. Great. Alkenes and alkynes are unsaturated hydrocarbons. That means they don't have all single bonds with hydrogens attached. Instead, they have double bonds. To name the molecule, you're going to do the exact same way that you did for alkenes. You're going to name the longest chain containing both the carbon atoms and the triple bond, but then you're going to end the name with YNE because it's an alkyne. So ethyne. Eth means 2 carbons, so ethyne is going to be 2 carbons with a triple bond in between. Just like with alkenes, give the carbon atoms in the triple bond the lowest number possible. So here's propyne. 1, 2, 3 carbons. Notice we don't have to say 1 propyne because there's only 3 carbons, so it's going to be assumed that you number this 1. Then you can have 1 butyne, 1, 2, 3, 4 carbons, or maybe 2 butyne. So notice it's the exact same way that we've done alkenes, except now we have a triple bond involved.